Welcome back to Igneous and Metamorphic Petrology. This is the first of 3 lectures that will focus on metamorphic facies and the application of metamorphic facies to metamorphosed mafic rocks. The concept of a metamorphic facies is foundational to our discussion of metamorphic rocks. Although Escala coined the term in 1915, Victor Goldschmidt was really the first to describe a metamorphic facies. Goldschmidt studied a series of contact metamorphic palitic, calcareous, and somatic hornfells of Paleozoic age in the Oslo region of southern Norway. Although the chemistry of the rocks varied considerably, Goldschmidt found that relatively simple mineralogy assemblages of fewer than 6 minerals in the inner zone of the aureole around the granitic intrusive. Goldschmidt was the first to note that the equilibrium mineral assemblage of a metamorphic rock could be related to the bulk composition. Aluminous pellites contained aluminum-rich minerals, such as cordierite, plagioclase, garnet, and/or an aluminosilicate polymorph. Calcareous rocks contained calcium or aluminum-poor mineral faces, such as diopside, wollastonite, and/or amphibole. From the correlation between the rock's chemical and mineralogical compositions, he concluded that these rocks in the inner aureole had to achieve equilibrium. Certain mineral pairs, such as anorthosite and hypersthene, were consistently persistent in the rocks of appropriate composition, whereas the compositionally equivalent pair, diopside and andalusite, was not. If 2 alternate assemblages are X-equivalent or compositional equivalent, we must be able to relate them by a reaction. In this case, the reaction is fairly simple. Enstatite plus anorthite equals diopside plus an aluminum silicate polymorph. Goldschmidt thus claimed that the left side of the reaction was stable under metamorphic conditions existing in Oslo. If equilibrium were not attained, perhaps either pair or all 4 minerals may have been found. Escala in 1914 and 1915 worked in similar hornfells in another region of southern Finland, where he confirmed the ideas of Goldschmidt by noting a consistent relationship between mineral assemblage and the chemical composition of a wide range of rock types. Many of the rocks of the assemblages were the same as in Oslo, although some rocks chemically equivalent to some in Oslo contained different mineral assemblages. Using strictly qualitative thermodynamic reasoning, he correctly deduced that the Finnish rocks, with a more hydrous nature and lower volume assemblage, equilibrated at lower temperatures and higher pressure than the Norwegian ones. In Escala in 1915, developed the concept for a metamorphic facies. In any rock or metamorphic formation which has arrived at an chemical equilibrium through metamorphism at constant pressures and temperatures conditions, the mineral composition is controlled only by the chemical composition. We are led to a general conception which the writer proposes we call metamorphic facies. At the time Escala made his proposal of the idea of metamorphic facies, the only way to describe and categorize metamorphic conditions were based on the interpretation of isograds, or the depth zones of Guberman 1904. These ideas were restrictive, and the new descriptions by Escala allowed for new interpretations since they were based on mafic rocks. Since mafic rocks occur in almost every orogenic belt, and the mineral assemblages in them define a broader temperature-pressure range, the facies idea provided a convenient way to describe and compare metamorphic rocks around the world. There was a dual basis for the facies concept, descriptive and interpretive. Descriptive is the relationship between the composition of the rock and its mineralogy. It's a fundamental feature of Escala's concept. A metamorphic facies is then a set of repeatedly associated metamorphic mineral assemblages. If we find a specified assemblage, or better yet, a group of compatible assemblages covering a range of compositions, while we're in the field, then a certain facies may be assigned to an area. The second basis is interpretive, a range in temperatures and pressure conditions represented by each facies. Escala was aware of the temperature-pressure implications of the concept, and he correctly deduced that the relative temperatures and pressures represented by the different facies that he proposed. Advances in experimental techniques and the accumulation of experimental and thermodynamic data have allowed us to assign relatively accurate temperature and pressure limits to individual facies. Eskla in 1920 proposed the 5 original facies: green schist, amphibolite, hornfels, sanitite, and eclogite. Each was easily identified and defined based on the distinctive mineral assemblages that developed in mafic rocks, clearly reflected in their facies names, most of which correspond to the common metamorphic rock type. In his final account, Eskla in 1939 added 3 more assemblages: granulites, epidote amphibolite, and glaucophane schist, which we now refer to as blue schist, and changed the names of the hornfels facies to the pyroxene hornfels facies. His facies and his estimates of their relative pressure and temperature relationships are illustrated in figure 25.1, and since then other facies have been proposed. The numerous other facies and even subfacies that have been proposed, but most have been dropped in favor of simplicity and ease of correlation. Now that we can assign pressure temperature limits to the facies types, we face a fundamental dilemma resulting from the dual basis behind the facies concept as we interpret facies today. Do we remain faithful to Eskla's original method of defining facies as a set of mineral assemblages, and restrict our choices of facies types only to those defined by the unique paragenesis in mafic rocks? Or do we rely on a modern ability to assign temperature and pressure limits to facies and stress the importance of these regimes? The metamorphic facies we shall use and their general acceptance in temperature and pressure are shown in figure 25.2. The boundaries between metamorphic facies represent pressure-temperature conditions in which key minerals in mafic rocks are either introduced or lost, changing the mineral assemblage observed. As a result, facies are separated by mineral reaction isograds. The facies limits are gradational and approximate because they vary with rock composition and the nature and composition of the intergranular fluids. The definitive mineral assemblages that characterize each facies, for mafic rocks in particular, are listed here in Table 25.1. As we go on to the next couple of videos, we will discuss in detail in the variations throughout the next couple weeks. It is convenient to consider metamorphic facies in 4 groups: high pressure, medium pressure, low pressure, and low grade. Facies of high pressure is our first facies set and consists of blue schist and eclogite facies, which are the facies characterized by low molar volume phases under conditions of high pressure. Blue schist facies are areas of low temperature pressure gradients, such as subduction zones. Eclogites are stable under normal geothermal conditions, such as deep crustal chambers or dikes, subcrustal magmatic underplates, subducted crust that is redistributed into the mantle. Facies of medium pressure are most exposed metamorphic rocks that belong to the green schist, amphibolite, or granulite facies. The green schist and amphibolite facies conform to the typical geothermal gradient. All 3 facies are also conform to elevated geotherms typical of most orogenic regions. Granulite facies occur predominantly in deep eroded continental cratons of Precambrian age. The facies of low pressure include the albite epidote hornfels, hornblende hornfels, and pyroxene hornfels facies, and are typically observed in contact metamorphic terrains, although they can also occur in regional terrains with very high geothermal gradients. The sanitite facies is rare and limited to xenoliths in basaltic magmas and the inner portions of some contact areoles adjacent to hot basaltic or anorthositic intrusives. Because the intrusions can stall at practically any depth and the orogenic geotherms are diverse, there is considerable overlap and gradation between the low pressure facies types and the corresponding medium pressure facies immediately below them in figure 25.2. Facies at low metamorphic grades contain rocks that occur at low grade facies that may fail to recrystallize thoroughly at very low grades, and equilibrium is typically not always obtained. The zeolite and propellite facies are thus not always represented, and the greenschist facies is the lowest grade developed in many regional terrains. The zeolite propellite facies are thus treated separately. These facies are best developed where the protolith is immature and susceptible to metamorphism, and where there is a high geothermal gradient and abundant hydrous fluids. As a result, they are most common in areas of burial or hydrothermal metamorphism. Due to the poorly developed mineral assemblage and the complex dependency of these facies types on mineral compositions, many geologists have given up trying to distinguish between them and have taken to using the subterm sub-greenschist facies to refer to them collectively. Putting all this together, we start to see that combining the concepts of isograds, zones, and facies is preferable. Metamorphic maps typically include isograds that define zones and ones that define facies boundaries. Determining a facies or a zone is most reliably done when several rocks of varying composition and mineralogy are available. This leads us to the concept and the idea of a facies series. Miyashiro extended the facies concept to encompass a broader progressive sequence, which is referred to as the facies series. A facies series is a traverse upgrade through the metamorphic terrains that should follow one of several possible metamorphic field gradients, and, if extensive enough, cross through a sequence of facies. The contrast between Miyashiro's high temperature, low pressure belt, as discussed in section 21.6.3 of your book, and the classical Bavarian sequence that we discussed with Escala also led him to suggest that more than one type of facies series is probable. In total, Miyashiro described 5 different facies series, most of them named for specifically representing type localities. These facies series include the Contact facies series, the Buckman facies series, the Bavarian facies series, the Sambagua facies series, and the Franciscan facies series. Metamorphic field gradients are highly variable, even those within the same metamorphic belt, and the transitional series are also abound. Miyashiro later chose to limit the number instead of to the 3 broad major types or facies series, illustrated in figure 25.3. Although these boundaries and gaps between them are somewhat artificial, the 3 facies series represent common types of tectonic environments. These different facies series, to include the 5 original series, will be discussed further in the next few videos. Our next video will focus on the facies series associated with the metamorphism of mafic rocks, specifically since these are the easiest to understand and the best understood. We will then follow up with reactions in metamorphic systems before moving on to other protoliths.